questions about the first lecture? So what we saw the basic properties of fluids. What is a fluid? What is not a fluid? How you can define a fluid, liquid and gases. And then we define viscosity. Sorry? Okay. So we define viscosity through a simple example. So how the shear stresses and the velocity gradients are related through the viscosity of the fluid. And we looked at we looked at the difference between a Newtonian fluid and a non-Newtonian fluid. Okay, so a Newtonian fluid viscosity is a constant. Non-Newtonian fluid viscosity is not a constant. It changes as a function of the velocity gradient. So there are two kinds of non-Newtonian fluids. Ones that are shear thinning and the other one that is shear thickening. So shear thinning, their viscosity decreases as long as the velocity gradient increases, and shear thickening, their viscosity increases as the velocity gradient increases, right? And then we looked at pressure. So we looked at static. We started looking at static conditions. Okay, in static conditions there are no shearing forces acting on the fluid, so there's no acceleration. So in order for the fluid to be in static conditions, all the forces in all the directions must be equal to 0, and the only force acting on the fluid is at normal to the surface of the fluid, and that is pressure. Okay, and so we made a simple example of point, and we find out that pressure is a scalar, it's not a vector, so it's isotropic no matter where.
Sir.
Yes.
Since we know up to now the quantity to be a vector, it should not obey the law of vector algebra, or it should not have both magnitude and direction. While proving the pressure, not the scalar, not the vector one, or it's a scalar, we just shown that it has the same value from every direction. So how these things are correlating, that I'm not getting the point that how pressure is a scalar.
Pressure does have a direction, so it Not sure I understand the question, but every point feels the same pressure at every direction. So the pressure doesn't depend on the direction. Okay. So if you shrink your element of fluid down to a point, it feels the same pressure in every direction. Okay. So pressure doesn't have a direction, a preferred direction.
Yeah.
Okay, so it's just a scalar. You don't have to specify the direction of the pressure, because it's just a scalar. Okay. So pressure at any point is independent of the direction as long as there are no shearing stresses. And now we're going to look at an infinitesimal volume of fluid. And make a similar example, but now we're going to consider the weight of the fluid. Okay. And we're going to adapt to the hydrostatic balance. So we're still in static conditions, okay? So there's no acceleration, there are no shear forces acting on the element of fluid. But now we're going to take a small element of fluid where we're going to have surface forces, and the only surface force acting on an element of fluid in static condition is pressure. And what we call a body force, which is something that we will define later, maybe Friday. And what is a body force in an element of fluid? Body force Okay, so in this case, the weight of the element of fluid. Okay, so we're going to take this small element of fluid. Okay, and we're going to look at pressure inside at the center of this element of fluid. Okay, so somewhere here. Okay. So we're going to look at the pressure inside of this element of fluid. So in this direction, what do we have? Now that's space. Then we have pressure, this direction, this direction, this direction, and of course the other two sides as well. Refer to the center of the element of fluid, we have pressure plus dp by dx. So this is dx, this is dz, and this is dy. Sorry, delta. dy, dz, okay, is a force by in the area, and is referenced to the center of the element of fluid. Okay, you can get this through Taylor expansion.
Please, is it dx over 2 or dx over z?
It's a 2. It's a number 2. So it's z. I would do it like this.
Oh.
Yeah, you see this?
Okay.
Because it's half of delta x, right? It's reference to the center of the element of fluid, so it's half of delta x. And here it's going to be the same, but dp dx dz. Here is going to be p plus dp by dz, z02, dx dy, and here is going to be p and the same for the other two sides. Okay, so the element is in equilibrium, it's not moving. Okay, so it's in static conditions. So the sum of all the forces must be equal to 0. So the sum of all the forces in the x direction will be equal to 0. So you do the sum of the two, and what is left is minus dp by dx dy dz dx. The sum of the forces in y, d in y is going to be x and y, and all the forces in the z direction dx, dy, and dz. Okay, it's just one minus the other, so we just left with the partial derivatives. So the sum of all the forces, delta F, is the sum of all the components which in this case is equal to per the element of fluid volume.
Why should the sum be delta instead of sigma? Why should it be delta instead of sigma?
Why should be
Sum of fx, sum of fy, sum of fz.
Sum of x, y.
I mean, I'm asking y should be delta instead of sigma, the normal sigma for sum.
Because all the increments in the forces in the x direction, all the forces in the y direction, all the forces in the z direction. Okay? It's of course the sum of all of them. So one and the other in on all the directions. So you're summing all of them, and what you're left with is this. So all the forces are going to be the sum of this. The sum of all the forces. Okay? Okay, so this is graph P, which actually we're going to define later, but doesn't matter. So this divided by the infinitesimal volume of the fluid is minus grad P. Okay? But what we have not considered yet is the weight of the infinitesimal volume of fluid, okay, which does exist. Which in this case is going to be, for the infinitesimal volume of fluid, is going to be this gamma times the volume of the fluid. And gamma is rho g, right? So Newton's second law, you have that F is mass times the acceleration. The mass of the infinitesimal volume of fluid is rho delta x, delta y, delta z. That's the element mass. So what we have is the sum of all the forces, delta F, minus the weight of the element of the fluid, which is directed downwards. It's going to be equal to mass times acceleration. So the sum of all the forces is minus grad P x, y, and z. Delta of the weight is minus gamma delta x, delta y, and delta z, and that's equal to the infinitesimal mass times the acceleration. Yeah, stop me if. It's pretty easy. Okay, we are in static conditions, and this is rho delta x, delta y, delta z acceleration. Okay. You can get rid of the infinitesimal volume of the fluid, minus grad P, minus gamma, rho times the acceleration. But we are in static conditions, so acceleration is equal to 0. The fluid is at rest, so A is equal to 0. So grad P is equal to minus gamma. Okay. Gamma has only one component.
The last statement, I didn't hear you.
The last?
Yeah,
Which one?
the very last.
From here?
Yeah.
From here. Okay, so all the forces on the infinitesimal volume of fluid are equal to minus grad P per unit volume. Okay? But then we have not considered the weight of the element of fluid, which is gamma times the element of fluid. So if we look at Newton's second law, F is equal to mass times the acceleration, and mass is rho times the element of fluid. Okay? So all the forces minus the weight, which is directed downwards, is going to be equal to mass times the acceleration. So the sum of all the forces is minus grad P times the element of fluid minus the weight, which is gamma the element volume, equal to mass times acceleration, or density times volume times acceleration. Okay? You get rid of the volume, minus grad P minus gamma, density times acceleration. Acceleration is equal to 0, because we are in static condition, the element of fluid is at rest. So grad P equal to minus gamma. Okay? Yeah? But gamma has only one component. Gamma is only in the vertical component. Okay? Is the weight. There's only one component in the vertical. So that means that if you expand the gradient, dp by dx equal dp to dy equal to 0, because gamma is 0 in the x and in the y component. So this reduces to and the minus. Okay. And this is the hydrostatic balance. Okay. Because this has only one component, this means that dp by dx equal dp by dy equals 0. Okay? Because dp by dx equal to 0, because this is 0 in the x component, dp by dy equal to 0, because this is 0 in the y component. So the only thing that is left is dp by dz equal to minus rho g in the vertical. Yeah, and this is called hydrostatic balance. Okay, so the pressure gradient in the vertical is balancing the weight of the fluid. In static condition, this is not moving, this is at rest. So the difference in pressure in the vertical is perfectly balanced. So the difference in the vertical in pressure is perfectly balancing the weight of the element.
The weight is acted only in the z direction.
The?
Acted only in the z direction. Z direction.
Who?
Weight.
Yes.
So if we deal weight individually with the z direction, for example, del Fg, I think it's del Fg is equals to minus del P by del G, del X del Y del Z plus weight. Since weight is in this direction, plus weight. So after that, if I incorporate this in the final expression, it's like del P plus del W is equals to del M into A. Is it so, or?
You said there should be a plus here.
Yeah.
No, it should be a minus because it's in the downward direction. So in this convection is minus.
Minus?
Yes. And positive
So
is
Z in
upward.
downward direction is minus. In this convention, Z in downward direction is negative or positive?
Is negative in this conversion Z component going down?
Now you're confusing me.
Because we find out the net force in Z direction by treating that G in negative downward direction as positive.
G is positive, but it's a minus because it's directed downwards in this case. So gamma is equal to minus rho g.
I will see.
I mean, it's correct, but
I have a question there. Why is the Z component below and that one minus? P minus of the infinitesimal period. Why is that negative minus?
You want to switch the signs, fine. So you want to put a plus here and a minus here.
No.
and a minus here and a plus here.
No,
Doesn't matter.
my question is, the one above is positive in the top area. So this one is the whole minus of P minus of, can you say like that? I don't understand why it's negative.
This and this.
That is positive, I agree.
This.
Mm-hmm.
Okay, because you're going up
Mm-hmm.
delta Z over 2.
Mm-hmm.
And here you're going down delta Z over 2.
Mm-hmm.
Okay? So you do one minus the other, P goes away. Okay? This minus this, the P goes away, this minus this becomes a plus, so dP dZ times dZ. Because it's twice dZ over 2. Delta X delta Y.
The signs for the other ones would have rather changed. So this is going that way.
Now I get the point.
Huh?
I get the point.
You get the point?
Yeah.
Okay.
Actually, we find out the net force, every component of the net force in negative of every direction. For example, we are finding the net force along the x direction,
Yes.
the negative one. That's right. And similarly for y also in negative, and z also in negative, and so there is minus del W in the final expression.
Or you can switch everything and you're gonna get the same result. Instead of having your coordinate system x, y, and z, you can have it like this. You switch out every sign and you're gonna get the same result. The point is that this is the hydrostatic balance. So you have a pressure gradient, okay, and you have a gravitational force or a body force given by the weight. They have opposite signs, so this is already telling you that the pressure gradient is going to go up, try to balancing the weight, which has a different sign. Or you can switch this. Okay, so this is the hydrostatic balance, or the pressure field in an element of fluid given given some weight. Now, static. Okay, so this is confusing, as you can see. There's a much more elegant way of showing the hydrostatic balance. Okay, well, it's not confusing. It's very simple. A much more elegant way of looking at the hydrostatic balance is using a theorem that we will look at today, I guess, which is the divergence theorem. Okay, so let's introduce a little bit the divergence theorem, and then we will look at it more closely. Okay. So the Gauss theorem, or for a vector field, is actually also called the divergence theorem. Relates the flow flux of a vector field through a surface. Okay, so you take a surface and you look at the flux of that vector field to the behavior of the vector field inside that surface. Okay, so if you have an outward flux or inward flux of a vector field through a closed surface, that is going to be equal to the volume integral of the divergence of the vector field inside the surface. Okay. What does that mean? Is that basically the sum of all the sources and sinks inside that closed surface. So if you have a vector field F, all the sources and sinks of that vector field F, so divergence or convergence, will be equal to the outward flux through the surface. Right? So if this is my surface, which is a closed surface, I have my divergence of F inside the closed surface, and that would be equal to the outward flux of my vector field. Okay, so basically if there is a divergence of the vector field, that will have to go through the boundary, and that is going to be equal. Okay, so the divergence of the vector field integrated over the volume is going to be equal to the flux of the vector field through the area. Okay? And of course, if you have convergence inside the volume, then you will have an inward flux of the vector field through the surface. Okay, so instead of having this element of fluid, let's take any arbitrary shape, okay, like a potato shape or whatever. And again, we're going to use body forces and surface forces, which is just pressure. So we have a element of the area and pressure acting on the element of the area. And then we have my weight of the element integrated with the volume. Okay? And we can call this rho F, where F is a body force integrated over the volume. Okay? So rho F is my body force per unit mass. Okay, so P is the surface force per unit area, as before, and the surface force vector is PdA, okay, which gives you the direction of the force. In static conditions, there is no acceleration, so all the body forces must be balancing the surface forces. So if we integrate the surface forces over the entire area, which is this, okay, this must be equal to rho F, correct?
I think the body force per unit area is only F.
The body force is only F, no.
Body force per unit mass. Because if we see the dimension...
Per unit, okay, sorry, per unit volume.
Per unit, okay. No, it's okay.
So I don't have to change it. Okay, so in static conditions, so the body forces have to be balancing the surface forces, because this is not moving. Now we can use the Gauss theorem. And the Gauss theorem says that this has to be equal to graph P, right? Yeah.
No, delta P. Sorry.
It's not a vector, it's a scalar, so it's not divergence, it's graph P. It's the gradient of P. Okay? So we can rewrite this as graph P dV is equal to dV rho F. And we can rewrite this as graph P minus rho F equal to 0. And for a continuous integrand, this is graph P equal to rho F. And we know that rho F is equal to rho minus GK and again this is the hydrostatic flux. Sorry, because it's only one component, so like this dP by dz. Yeah? So it's much faster and cleaner to derive the hydrostatic balance using the Gauss theorem. Okay, you can take any volume of your element of fluid. It's in static conditions, so there's only pressure acting on the surface, and the force is P dA. You can integrate over the whole surface this force, this pressure, which is this, and this must be equal and balanced by the body force. And you can integrate over the whole volume your body force, rho F. Okay, so the two.
What's F?
F is my body force.
Okay.
In this case, my body force is G, is gravitation, but it could be an electromagnetic field. Okay. So F is minus GK.
Okay.
Okay. Just to generalize the body force. So these two have to be equal. So from here to here, I use the Gauss theorem. So I get two volume integrals. Okay. So the surface integral of pressure is equal to the volume integral of grad P. It's not a divergence because it's a scalar.
And please, can you say that last statement again?
This one.
Yeah.
So we use the Gauss theorem here. Okay. So we go from a surface integral to a volume integral. So the surface integral of my vector field is equal to the volume integral of the divergence of the field. In this case is a scalar, so it's the gradient of the pressure. Okay. So the surface integral of pressure is equal to the volume integral of the gradient of pressure. So I go from the surface integral of pressure to the volume integral of gradient of pressure. So the volume integral of the gradient of pressure is equal to the volume integral of the body force. Okay. So there's only one volume integral of grad P minus rho F, and that must be equal to 0 because we're in static condition. Okay. So this means that for a continuous integrand, grad P must be equal to rho F. But we know that rho F in this case is a body force, which is gravitation. So that's minus GK with only one component in the vertical. So grad P reduces to dP by dz equal to minus rho G. Okay, so this is a lot about the pressure because you're gonna see a lot of hydrostatic balances in all your courses, and we just introduced the Gauss theorem. And to continue talking about pressures, now we're gonna look at how we can define pressures in fluids. Incompressibles and compressible fluids. Okay, so we're still in static conditions, we're still not talking about stresses, the surface. But now we're going to look at the pressure in incompressible fluids. Okay, so in incompressible fluids, gamma, which is rho G, in a good approximation is a constant. Okay. Because it's incompressible. And so that's a good approximation in liquids, for example. Okay. Liquids are not very compressible. So we have our hydrostatic balance. Okay, for an incompressible fluid, we know where the hydrostatic balance is coming from. And now we can integrate this from some P1 to some P2. And that is going to be equal to my gamma from some Z1 to some Z2. So this is going to be P2 minus P1 equal to minus gamma Z2 minus Z1. Right? So now we're going to take P1 as a reference pressure. Okay, so we're going to call P1 equal P naught, some reference pressure. That is going to be 0. So we have P minus P naught is going to be equal to minus gamma Z2 minus Z naught, a reference level. So P naught, for example, can be the atmospheric pressure, okay, at the surface, and that is going to be my reference. So if that's my reference, then I have P equal to gamma H, where H is Z2 minus Z naught, so the height of my fluid. Okay, and there's a switching sign because I'm talking about liquid and I'm thinking about the ocean. So I have P at the atmosphere, and I have some height going down into the liquid. Okay, so Z2 minus Z naught, it's minus H, minus and minus have a plus. And H is called the pressure head. Okay, so it's depending on the height of the fluid, that is going to be the pressure head, or the increments in pressure due to the height of the fluid,
Why do you
or how deep you're going into the fluid.
the P not the atmospheric pressure? P minus P not is
Because P naught, which is my atmospheric pressure, could be 1,000, could be 1 million, could be whatever. That's going to be my reference level. So that's going to be 0.
okay.
Okay. So imagine. So if you look at some isobars, for example, in the atmosphere. Okay. So the atmospheric pressure. I don't know. For example, this is not going to be a good example. But for example, you have your reference level, your reference pressure is this one, which is 1,000 decibars, whatever, okay? And this is 1,010, and this is 1,020, okay? So that would be, 1,020 would be P2, and 1,000 is P1, my reference, okay? So instead of writing that, I say, this is 0, this is 10, and this is 20. Okay, because that's my reference. So P naught or P atmosphere disappears. Okay. So I'm left with the pressure, which is referenced to the atmospheric pressure, is equal to gamma, and then the difference in height. And this difference in height is called the pressure head. Okay, so how much you're going into the atmosphere or how much you're going into the fluid, that height will determine the change in pressure. Okay.
So, instead of also assuming the pressure to be 0, can you also define the new pressure as a gauge pressure where you maintain P minus P naught?
That's coming in 2.5 minutes. Okay, so this is for incompressible fluids. Okay, the pressure is equal to gamma times the pressure head. Easy.
Sorry, one second.
That's good, that's good.
Why did you, the minus, what's happening?
Because Z2 minus Z0 is negative,
Okay.
okay, in this case.
Okay.
Now for compressible fluids, for example air, where the density is a function of the pressure, so the density is a function of the pressure as you go up in the atmosphere, for example. Then in that case, we use the perfect gas. P equal rho RT, okay? R is the gas constant, P is the absolute pressure, and T is the absolute temperature. So we go back to our hydrostatic balance, and we substitute here minus P over RTG. Okay, substituting with the perfect gas.
Are we assuming a dry gas? Because this equation goes for only the dry gas.
These are just simple examples. Now we can separate the variables. So we take dP over P. We integrate over P1 to P2 minus G over R, Z2, Z1, dZ over T. Okay, just separating the variables. This is going to be equal to ln of P2, P1 equal to minus G over R, Z2, Z1, dZT over T. Okay, now we assume a constant temperature T0 to make it very easy and very simple. Okay, we assume the temperature has a constant temperature T0. So what we're going to derive is the relationship for an isothermal layer, so a layer of constant temperature. Okay? So we assume the temperature is constant with some T0. So this is a constant. So this becomes ln of P2 P1 equal to minus GR T0 Z2 minus Z1. So this is simply P2 equal to P1 X of minus G, Z2 minus Z1, R T0. Okay, so for an isothermal layer, so this is a very idealized solution, a layer. This is the relationship between pressure and height. Okay, before we had P equal gamma H. Okay, the relationship between the pressure and the height, or the pressure head. Now you can substitute this with H, if you like. And you can switch the sign, or H equal to minus H. But
Why didn't we assume a pressure, reference pressure for this one, as we did for the incompressible fluids?
you could. P1 is my reference pressure, which could be the atmospheric pressure. You seem disappointed. Okay, so as you were saying before, you can also define an absolute pressure. If you don't want to define a reference pressure, as we didn't in this case, the pressure absolute is going to be equal to rho GH, plus the atmospheric pressure. If I didn't cancel out the P1, which was equal to P0 or P atmosphere, okay, now it would be P2 equal, okay. So I can define my absolute pressure, not reference to some reference level, reference pressure. The absolute pressure is this, which is gauge pressure plus the atmospheric pressure. And H is the height of the fluid or the head of the fluid.
Does
Yes.
the absolute pressure work for both fluids or just the incompressible fluid?
It works for both.
Both.
Yeah. Instead of, as you go down into the, for example, the ocean, you can reference everything to the atmospheric pressure or not. So whatever pressure, the absolute pressure is going to be the gauge pressure plus the atmospheric pressure that you have on the surface.
Sir, even the atmospheric pressure is also dependent on height or depth of the system. So can you write the general expression for absolute pressure is rho gs, and so define the as
Rho G,
as
heads. But then you don't have any reference. You don't have any. Well, maybe this is going to help you. In a second. So, well, this is just so for incompressible fluid, P minus P0, your reference level, applies to liquids. Pressure related to the height H of the fluid, that's the pressure head. Okay. So maybe you were mentioning this. Okay. So the difference between absolute and gauge pressure. So the absolute is relative to an absolute zero perfect vacuum. Okay. So the absolute pressure, PABS, is this one. Okay. Which includes the gauge pressure and the atmospheric pressure. The atmospheric pressure varies, of course, but in one point in space and time, that's the atmospheric pressure, and then you measure the gauge pressure. So you have gauge plus the atmospheric pressure. But the absolute is relative to the absolute zero. Okay. And then you have the atmospheric pressure, and you could have actually a vacuum. Okay. Is that what you meant?
so the dependency of atmospheric pressure and that the gauge pressure is different, has different behavior with the depth. They are not dependent with the depth in the similar manner. That's why we have to write with the additive one, this and this. Otherwise, we can write with the single term.
Sure. I mean, well, you measure absolute pressure, and the absolute pressure in one particular space and time is made of two components. The atmospheric pressure, for example, at some level, the surface of the Earth or the surface of the ocean, plus the gauge pressure, which is telling you how much head or height you are into the fluid. Okay, so the atmospheric pressure reference to the floor has a value right now in this place, and here there is a compressible fluid, air. Okay. So the absolute pressure here and the absolute pressure here is supposed to be different, okay? Because the head or the height in this case is atmospheric pressure plus H, the head, okay? And here H is different, so you want to measure this reference to the atmospheric pressure, which is at the floor. If you go somewhere else, the atmospheric pressure at the floor is going to be different, of course. You could write the absolute pressure here has a value, and the absolute pressure in town has a different value. which is made of two components, the gauge pressure and the atmospheric pressure. So the atmospheric pressure, which is measured at the surface level of your system, plus the gauge pressure, which is telling you how much head or how much height you are into the fluid. Could be air, or could be water, or could be any other fluid.
Sorry? So, just to be clear, your definition of incompressible fluid is constant specific weight.
Density doesn't depend on pressure.
Density.
Okay. For compressible fluids, density is a function of pressure, so it is compressible. You don't like this definition?
No, it wasn't just very clear at the beginning. It wasn't clear.
So air is very compressible. Okay, so it's a compressible fluid. Density varies a lot with pressure. Right? It's a fluid that is very compressible. Water is a fluid that is not very compressible. So it's a good approximation to call it incompressible fluid. Pressure has an effect on density, but it's very small compared to air.
Yes.
Okay, so atmospheric pressure, which is what we've been talking about, is also called the barometric pressure. Okay, so and it's 1 bar is equal to 10 to the 5 Pascal. Okay. Divided with elevation, location, changes in meteorological conditions. So this atmospheric pressure is not constant, of course. Okay. But then you want to reference the pressure that you measure to that atmospheric pressure. Absolute pressure is used for most problems related to gases and vapor, and the gauge pressure is usually used for liquids, like in the ocean. Okay, now we're gonna show another nice example still related to pressure, okay, which is called the Pascal law. And that's Pascal, of course. Okay, so all points in a connected body of constant density, fluid, at rest, so we're still in static conditions, are under the same pressure if they are the same depth below the liquid surface, okay, because we saw that pressure is related to the head of the fluid. Okay, so if you are at the same depth, here and here, pressure is going to be the same, right? Because it's related to the height or the head of the fluid. Okay. So if it's a connected body of constant density, so density doesn't have to change. Okay. So this density ρ1 is constant throughout this system. Okay. So density is constant. The fluid is connected, of course. The fluid is at rest, we're in static conditions, so you have hydrostatic balance. So every point in this fluid has the same pressure as long as they are the same depth of the liquid surface. Okay? So P1 and P2 are the same, if this is the same, if this is the same height or the same head. So a nice application of this is, so we're in static condition, so there are no shear forces, we're in static condition. So we know that P1 is equal to P2. Okay. And now we assume there is a force here, F1. And this is a connected body of fluid, so there's going to be a force, F2, on the other side. Okay. Then we have this area, which we're going to call A1, and this area that we're going to call A2. Okay. And A2 is much larger than A1. Okay. So the pressure is the same, so F1 over A1 is going to be equal to F2 over A2, because the pressure is going to be the same. But because A2 is much larger than A1, this means that F2 is much larger than F1. And this is called multiplication of forces. Okay, so basically we are applying a force F1 to this small area A1. And because the pressure at every level is the same and we are in static condition, this F1 over A1 has to be equal to F2 over A2. And because A1 is much smaller than A2, in order for these two to be the same, F2 has to be much larger than F1 in order to be the same. So how big is F2? F2 is A2 over A1, F1. So it depends on the ratio between the two areas. Now we can look at work. The work done by this force, which is force times space, which is 1 Newton times, for example, meter, which is 1 joule. Okay? So the two work has to be the same. So work 1 has to be equal to work 2. This means that F1 D1, and D1 is, for example, this, will have to be equal to F2 D2, and D2 is, for example, this. Okay. So D1 is F2 over F1 D2, or because of this, A2 over A1 D2. So, because we know the ratio of these two, then this means that D1 is much larger than D2. Okay, so what I'm trying to say here is that using static conditions and the hydrostatic balance, and the fact that pressure at every point in this fluid has to be equal as long as the height or the head is the same and the fluid is connected, if we apply a force over this small area, there would be an equal pressure on the other side equal to F2 over the area A2. Okay? This. Okay. And because A2 is much larger than A1, then F2 will have to be much larger than F1. Okay? So that's why the multiplication of the forces. Okay? With a small force F1, you generate a large force F2 on the other side because the area is much larger and the pressure has to be the same. If you look at work, so the force times space, F1 D1, so how much you're pushing the fluid down, will have to be equal to F2 D2, how much this is going up. Okay? And because the ratio between F1 and F2, you end up with D1, this, that has to be much larger than D2. So this is basically the price to pay, if you want, okay, to maintain the same pressure on the other side. Okay. An example of this, you might think, why is this guy telling me this? Okay, it's a nice application of hydrostatic balance and static condition, which is used in many, many applications. For example, this is just what I was trying to draw on the board. Okay, this is what happens every time you go to a garage or a mechanic. Okay, they use what is called a hydraulic lift. Okay, and they use the hydrostatic balance. So basically, when you're trying to lift your car, you go over some plate, okay, and there is a long tube underneath, under the floor, which is filled with some liquid, okay, and the guy applies a force on one side of the tube over a small area, and it generates a much larger force on the other side of the tube, which has a larger area, it's a big plate, okay, and this strong force is able to lift the car, okay, with a relatively small force on this side. The price to pay is that this D1, okay, so how much you have to push the liquid into the system, this D1 has to be much larger than D2, okay. So if you use a diameter here, D1, which is, for example, 1.25 centimeters, or something you can do with your fingers, and the diameter on the other side is 25 centimeters in order to lift your car. The area A1 is this, A2 is that, the ratio is this, so the ratio between F2 and F1 is a multiplication of 400, okay? So if the car is 6,000 Newton, F1 will have to be 15 Newton, okay? So in order to lift a car of 6,000 Newton, you just need 15 Newton on the other side. But how can you do that? You can do that only if D1 is much larger than D2. Okay. So in order to lift it 10 centimeters, so D2 10 centimeters, you're gonna need a tube that is 40 meter long. Okay. So underneath the garage there's a long tube. Okay. And that's the 40 meter long tube. Well, no, they don't do it like this anymore, but that's what you would need. Okay. A 40 meter long D1 in order to lift the car 15 centimeters, okay, in order to maintain the two work equal. But that's a nice application of hydrostatic balance. No questions, I guess. So still on the hydrostatic balance, is the buoyancy force. Okay, remember dV by dz is equal to minus rho g, my hydrostatic balance. Okay, so we know that pressure in the atmosphere decreases with height. Okay, if this is my height, pressure decreases with height. Okay, this is my pressure as a function of z. Okay. And so there's a pressure force, for example, on a balloon. Okay. And what is buoyancy force? The buoyancy force is the difference between pressure here and the pressure there. Okay. And the pressure at the bottom is greater than the pressure at the top, so that the buoyancy force is going to be equal to pressure at the bottom minus pressure at the top. Because pressure varies with height. Okay? So there's always a buoyancy force in every fluid, and it's always positive because this is positive. Okay? Pressure at the bottom is larger than pressure at the top. If you think of the ocean, and now z is directed downwards, pressure varies this. Okay. Pressure increases as you go deep into the ocean. And pressure at the bottom minus pressure at the top is again positive. Okay. So there's always a pressure, there's always a buoyancy force in every fluid, and it's always directed upwards. So what is buoyancy for the fluid? It's a force exerted by a fluid that opposes an object's weight. Okay, because this balloon we didn't consider yet that has a weight. Okay, so the buoyancy force is directed upwards, and the weight is directed downwards. Okay, so this buoyancy force is trying to oppose the weight of the object or the fluids. Okay, force is equal to the weight of. Okay, so what is this buoyancy force? This buoyancy force is equal to the weight of the fluid displaced by the object. Okay, so if you imagine that ball there, raw object, okay, raw object inside a raw fluid. Okay. So the buoyancy force is equal to the weight of the fluid, so the density of the fluid times gravity times the volume displaced by the object. In this case, the whole thing is immersed in the fluid, like a balloon in the atmosphere. Okay. So the buoyancy force is given by the density of the fluid, not the density of the object. Okay? So the object, if you put a ball into the ocean, it will feel a buoyancy force that is equal to the density of the fluid times gravity times the volume displaced by the object. Okay? If the object, like in that case, was not totally into the fluid, this, okay, there will be only this volume of the object, okay, because this object is displacing this much of fluid. So density of the fluid displaced times the gravity times the volume displaced by the object. That's how much buoyancy force the fluid is giving to the object. So an object whose density or specific weight is greater than that of the fluid in which it is submerged tends to sink, okay? Because the buoyancy force is related to the density of the fluid, and the weight of the object is related to the density of the object, of course. Okay? So if the density of the object is, or the specific weight is larger than that of the fluid, the weight will be larger than the buoyancy force. Yep.
Sorry, again?
Again and again. Yeah. I have a few examples. So let's put it inside of the fluid. Raw object, volume object, raw fluid. Okay? So the weight of the object, mass times gravity, in static condition, in equilibrium. So this object is not sinking and is not rising into the atmosphere or into the ocean. Okay? It's static. So the buoyancy force that is trying to lift the object is equal to the weight of the object. Okay? So mass times gravity is equal to density times the volume displaced, which is, in this case, the total volume, times gravity is equal to 0. That's right. So if the buoyancy of an object exceeds its weight, it tends to rise. If an object whose weight exceeds its buoyancy, it tends to sink. I thought this was pretty obvious. No, you seem confused. If I throw myself, okay, so that's an example. Is it easier to float in a pool or at sea? Okay, so you swim in a swimming pool. Okay, this is my swimming pool, and I'm swimming. Okay, totally into the water. Let's say. Okay, so I'm displacing this much volume. So the buoyancy force that is trying to lift me is going to be equal to my volume, because I'm totally into the fluid, times the density of water, the fluid, okay, times gravity. Okay? This is the buoyancy force that is trying to lift me up. And then I have my own weight. Okay? At sea, the buoyancy force is going to be my volume times rho density of the sea times gravity. Okay? In static condition, me minus buoyancy force is equal to 0. Okay? I don't sink and I don't rise to the surface. But now buoyancy force can change because it depends on the density of the fluid. Okay? So me minus buoyancy force equal to me is always me. Okay, swimming. If I swim in a swimming pool, I have the density of the fresh water. If I swim at sea, the buoyancy force is proportional to the density of the sea. Okay? And the density of the sea is higher than the density of fresh water. Okay? So the buoyancy force that I feel when I swim at sea is going to be higher. So is it easier to float in a swimming pool or in the sea? In the sea is much easier because the buoyancy force that you feel is much larger. Because the buoyancy force depends on how much volume you displace. Okay, and let's say that I'm always inside of the fluid totally. Okay, so the volume is always the same, G is always the same, but then the buoyancy force that I feel is proportional to the density of the fluid that I'm displacing. So if I'm displacing seawater, the buoyancy force is going to be larger than if I'm displacing fresh water. So buoyancy force is going to be greater. So it's easier to float at sea.
If the water is made by same components, so I think the density will be the same.
Of course, yes. If the density is the same, then the buoyancy force is the same.
It depends on the sea or pool or the
okay. So what I meant is that in a swimming pool, water is fresh water. There is no salt. It's water that you can drink, like drinking water, let's say. And at sea is seawater. Seawater has salinity, it has salts. Therefore, the density is higher. So if the density is higher, the buoyancy force is going to be larger.
So when you are maintaining the volume as a constant, I was thinking if you are displacing in the swimming pool, you have a boundary, you have a level to which you can displace, but at the sea it is infinite. Can't it also play a role?
Let's move on. Well, I'm going to have you more examples to convince you. Okay, more funny examples. So this is Archimedes' principle. I mean, this is high school things. Okay, Archimedes' principle says that the upward, okay, it's always upward buoyancy force that is exerted on a body immersed in a fluid, whether fully or partially. So V could be my total volume or some partial volume of myself, is equal to the weight of the fluid, so rho G, that the body displaces. Okay? I don't know if you know the story that Archimedes, somebody went to Archimedes and said, you have to find out if this crown is made of pure gold or a mixture of gold and another metal, but don't break the crown. So what he did is he put the crown into a fluid, and one crown made of pure gold, and the crown that he had to find out if it was pure gold or not. Huh?
Iron pirate. It's no.
Okay. And he found out that the crown was not made of pure gold because the mass was different, the buoyancy force was the same because he was displacing the same amount of volume. So the buoyancy force was the same, but the weight of the two crowns was different, and that's because one was pure gold and the other one was not pure gold.
Yeah.
Was that so? Yeah?
Yes, iron pyrite. The material was iron pyrite, so it was almost fool's gold.
Yeah. And so this brings me to the other example, materials of human body. Okay, density kilogram per liter. Okay, muscles is I don't know where I got these numbers. Muscles is 1.1. Bone is 1.5. Okay, it's more dense. And air that we have inside our lungs is 0.0012. Whatever. So in fresh water, in a swimming pool, if I breathe all my air out, so I empty my lungs, men usually men have more muscles, okay, and their bones is heavier. So for the same amount of volume displaced, our weight is higher, and so we tend to sink. Women in the same fluid, they usually have less muscles, their bones are usually less dense. If they breathe out all their air in the lungs, they tend to sink. Okay? Same buoyancy force, same volume of men and women. Okay? Two persons, they have the same volume, but their composition is different, so their specific weight is different. So men usually tend to sink, and women tend to float in a swimming pool. Okay? Again, in a swimming pool, if we keep our air in, so we reduce our density, okay, and that's going to bring me to the next example. So if we keep our air in, so we reduce the density, men, some of us will sink, okay, and women all will tend to float, okay. So this is a stupid example, but I'm trying to introduce the next example, which is a real one. So you can change the density of your volume, okay, and by changing the density of your volume, keeping the same volume and therefore the same buoyancy force, you can be an object that tends to sink or an object that tends to float. Okay, so it's all about how dense you are, given the same volume.
So here, there is no way for a woman to sink.
There is no what? You want to sink who?
Yeah, because in other cases, men
we sink.
we sink.
We all sink. We all sink, or some of us will sink. But if you...
No, women.
Huh? You want to sink women? Should I stop the recording?
Sorry. The formula maybe negative.
Yeah. So there's supposed to be a minus. Okay. The balance between the two in static condition will be 0. Okay. Or you put a minus on the other side. Okay. That's a type. Okay, so that's exactly, I mean, this silly examples is exactly what people is using in everyday life, okay? So why a boat is floating is something that, my children ask me, why is this boat floating? So, Archimedes' principle is buoyancy force, it's simple. So if you throw a block of iron, or it's like when you hear somebody say, when they see a large container like this, when they see a large container in the sea, and they think, I don't understand why that big thing is floating. Well, it's pretty easy. Okay, it's pretty easy why they float. Okay, it's just about buoyancy. So if you throw a block of iron in the water, it will sink. Okay, that's it. If you throw the same volume of wood in the water, it will float. And that's because the density of the wood is much less than the density of the water. They displace the same amount of water, so the buoyancy force is the same, but one has a specific weight that is much larger than the other one. Okay? So if you have a boat, okay, the boat is less dense than the water because the boat, what is below the water, is not filled with concrete iron, it's not packed with iron, it's actually empty. There are some empty chambers in order to reduce the density. Okay? So the boat is less dense than the water, so it displaces a mass equal to its own instead of sinking. Okay? So this water is displacing this volume. Okay? So the buoyancy force that is experiencing is density of the water times g times this volume. Okay? And that will have to be equal, in order for the boat to float, that will have to be equal to mg of the boat. Okay? So buoyancy is thus related to the density and the volume of the object. Okay? You don't want to be too dense, like a block of iron, otherwise you will not float. So the buoyancy force is rho of the fluid times g times the volume displaced. So what is the volume of the displaced water in stationarity? The weight of the boat has to be equal to the buoyancy force, so rho times g times volume displaced. So whatever is underwater is equal to the volume of the weight of the boat over rho g. Okay, so you have to play with rho, with the density, in order to have the boat more or less floating and not sinking. So this case, okay, which is what we're doing, as you can see, this ship is floating too much. Okay, and why is this ship floating too much? Because this ship is empty. Okay, when this ship will be packed with containers, it will increase its weight and its density, and so it will sink until the red line. When it goes down to the red line, they will stop carrying containers. Otherwise, the specific weight of the boat will be larger than the buoyancy force. Okay. So that red line marks the limit of the buoyancy. Okay. When it's empty, the buoyancy force is much larger than the specific weight of the boat, so the boat floats actually almost too much. Okay, it's just playing with it. It's just playing with the density of the.
What is that responsible for a boat or ship capsizing? Like, what causes that?
Terrible captain. And another nice example of buoyancy and buoyancy force is this one. So this is an oceanographic example, okay? And I have 4 minutes for this. So this is an instrument that oceanographers use to measure the ocean. And if they want to measure the ocean inside of the ocean, okay, they have built this instrument which is called an Argo float. Okay, which is that big thing, yellow, like this. Okay, and that Argo float is filled with a liquid. Okay, and what they can do is they can program the Argo float to change its density by increasing the pressure. Okay, so what they actually do is they say, okay, I want to measure. This is 1,000 meter. This is 2,000 meter, and this is 3,000 meter, for example. Okay, into the ocean. Somebody says, okay, I want to measure temperature, salinity, velocity, oxygen, many things, roughly at 2,000 meters depth. Okay, so they program this Argo float to be buoyant at 2,000 meter depth. So they throw this instrument in the water, and it will start to sink until it finds its own level of buoyancy, which, as it was programmed, is 2,000 meters. So at 2,000 meters, its weight is going to be balanced by the buoyancy force that is experiencing. Okay, so it stays there, it becomes buoyant at 2000 meters depth. And it moves by the current. Every 7 days or so, it is programmed to change its buoyancy and to acquire buoyancy, so it becomes less dense. The buoyancy force is still the same because it's the volume displaced times the density of the fluid times g. So buoyancy force stays the same. The weight changes. So this Argo float goes back to the surface, okay? Because the buoyancy force is much larger than the weight. Once it goes back to the surface, through that antenna, it sends all the data to a satellite. And when it's done sending all the data to a satellite, it is programmed to recover the original weight. So it will start to sink again down to the level of buoyancy. Okay? And it will start moving again at 2000 meters depth. So they just use the buoyancy force in order to measure temperature, salinity, velocity, whatever in this instrument.
What happens to it after measurement? After the measurement is done, what happens to it? Is it left on the ocean?
All those black dots that you see there were Argo floats. Oh, I took 2018 instead of 2019. Sorry. So I should update this figure. So every black dot is one Argo float that was exactly 1 year ago in the ocean. 3,964 floats. Okay. Every one of that single dot is a different level. Okay, because one float is programmed to be at 2,000 meters, another float is programmed to be at 1,000 meters, so on. So they move with the currents. So basically, you throw your instrument wherever you like. It will go down to the level where it is programmed to be buoyant, and then is affected by the flow. Every 7 days, it goes back to the surface, sends the data, and then goes back to its own level of buoyancy. And it stays there for as long as the battery is alive. And then if you're lucky, you recover the Argo float, and if you're not lucky, you don't recover the Argo float.
Is that for the certain instant of time, the snapshot?
That snapshot is for what?
At any instant of time, for example, time.
If I look at the today, or we can do it right now, the dots will be in a different position. Is that the question?
Yeah.
Yeah. So that day the dots were there.
Okay.
Today. Okay, this is today. Okay. There are 3,852 floats right now in the ocean, and well, yesterday they were there at different depths.
You mean is it 3,852 Argo floats?
Yes, all those black dots
Oh.
in total are 3,852. Yeah, as of yesterday.
Interesting.
And if you go on this website, argo.ucsd.edu, you can download the data, all the data are for free. So you can get all the data that those Argo floats are collecting. Temperature, salinity, velocity, direction of the flow. Some of them measure oxygen, chlorophyll, things like that.
So
All the data are freely available.
what makes the float to go up after a measurement? Is it the program?
It is programmed to lose its buoyancy, or to gain buoyancy,
Mm.
so to change its density
Okay.
every 7 days or so.
Mm.
So every 7 days it gains buoyancy, changes the density. So the buoyancy force is the same, but the weight is less.
Yeah.
So it goes back to the surface.
Why does it have to communicate with the satellite, or it has to transmit the data to the satellite?
It has to transmit the data to the satellite. It cannot keep all the data for a year in its own memory.
So for that case, it takes 1 day to transmit the data.
I don't know how much it takes. It might take an hour. I don't know. I don't use this float. I don't know. You can probably read it on the website. It probably takes a long time to go back to the surface, transmit all the data, then acquire again lose buoyancy, and then slowly go down to 2,000 meters. It might take 1 or 2 days, the whole process. But that's a nice application of the buoyancy force. And I'm done.
I'm going down to this level. And this level, I'm not thinking anymore.
Actually, the Argo is programmed in such a way that it changes buoyancy while going down, and just settle here where we are going.
Okay.
Actually,
Well,
interested to calculate.
If I'm started thinking this here, in here, there is no difference between buoyancy force.
No. Inside Argo,
No, it's just me.
volume. Yeah.
My volume is the same.
Yeah.
G is the same,
Yeah.
rho is the same. So if I start to think, I go to the bottom of the sea. Yeah? Is it true? Or I stop thinking somewhere between the ocean?
No, I'm not getting it right.
No, I mean that this is the ocean, okay? And I'm going to sink in the ocean, okay? My volume, no change, fixed. G is fixed and rho is fixed. I mean, if I start to thinking, I'm going to the bottom of the sea. Or no, the buoyancy force depends to the depths of the sea. So here, the buoyancy is much greater than here, and I'm not thinking anymore. No?
Actually, for the specifically for you, your buoyancy force is fixed initially. So the condition when you jump to the sea, you go up to the position where your force, buoyancy force, and your weight get balanced. You know, that's the case. You go somewhere, just do like this, and you finally come into the position where your buoyancy force and the weight equilibrates.
Okay, but you say that buoyancy force here and here the same. It's not the same?
Yes, same. But I wanted to. It's just a static case. But when you jump into the sea, it's instantly the condition is not coming. You know, for example, the condition for equilibrium comes after some time. You know,
yeah.
When you dip the egg into the water, first egg just go to the bottom and come and come. Finally, it comes in the position at where it's in the equilibrium, and the equilibrium position determines by the buoyancy force of the egg and weight of the egg. Buoyancy force on the egg and weight of the egg. That's the exactly case for you when you go to the sea. But
you mean
in
the
this case,
buoyancy force should be equal to the weight? That's the equilibrium.
No, not sometimes, always that, you know. That's why it determines you sink, float, or you are in somewhere between the depth. That's determined by the how greater the buoyancy force with the weight and with weight with the buoyancy force.
This is okay if the object is at equilibrium, but if it is still going, this is not equal. The weight is greater than the buoyancy force. At the point it will stop in the water. At that point, the buoyancy force is equal to the weight.
You get? You get?
If object enter in the sea, it goes.
Okay, my weight is fixed. My weight is not changing.
For this object, he said it is
programmable. Not about this. About me.
Yeah.
For you, you will reach at a point.
Why I'm going to the it's the ocean. Why I'm going to think here, and this is the equilibrium position. Why the equilibrium position is not here? Why it's not here? Why you say that this my weight is not changing? There is no changing in my weight, and there is no changing in force of equilibrium.
Yeah, that's why when you jump in the sea, you are in some position that how determined by the buoyancy and the weight. For example, your weight is mass g, yeah, and it's rho of body, your body times volume of your body times g.
Exactly.
And buoyancy force is rho of water that you dip or see g times volume that you displaced.
Exactly.
So indeed, to find out your position, we can subtract. For example, if this is the system, you know, and you are here, and this is weight always acts in the downward direction. This is buoyancy force. It always acts in the upward direction. That's why. Where are you? It's determined by FV minus what. Where are you? And it's indeed G is constant. B displaced and B body is same because you displace the volume that exactly So G volume displaced for this case, you know, the only difference is rho of water minus rho of body. So where are you? It's determined by these parameters. If rho of water is greater than the rho of your density of your body, then it will be positive. So what's happening? The buoyancy force is greater than the weight, so you float. Yeah. If rho of water is less than rho body, you sink. You go deep. And if they equals, then you are in somewhere that it equilibrates. So, but whatever the case, for example, you are in this case. For example, your body density of body is less than the density of water. For your case, you have to float. But when you jump in the sea, you are always not instantly float. Initially you deep, and after all like that, and finally you come in the floating condition. That's why it's not the instant case. I think your confusion is that you think like you know they are same, they are fixed. When I go down, and so I think you're is it?
Exactly. Thank you. It's good. Thanks. Guys, thank you. See you Friday. You sent the paper?
No, it's still
You
not.
sent the paper?
Actually, Hamid,
Yeah?
it's very, very, very tough for me, you know, finding the paper. And even I did not give
so
the.
do I know that, you know.
But you know, I hope you are very good in that subject.
Come on.
Because you know everything, man.
Come on.
I-
You are
I
the best
sent-
physician, I know that. you sent?
I sent, but I don't know if he will accept.
No one.
You understand the paper then? Pardon. You
I
understand?
don't know, and I don't understand where the paper.
You don't understand the content of the paper still that you sent?
I don't understand well.
Well,
Yeah.
Okay, see.
Okay, see you.
See you.
How are you? Ah, we don't have that. We don't have that. We only have like 2 minutes before right there. We have like 20 minutes. Ah, this is a delay. Oh, so we still have a chance to have our. What? Someone, he came like a few days ago, right? This one was not even selected. This one has a case exactly like this. What is it? She was here for workshop. Oh. She was a master student. Then she knew that there are positions that already being left. So she asked if she can fill that. Ah, yeah. Yes, this is very nice. Because they have the money. Because she told me that like before 1 hour, like at the last minute, after even being the ticket for these people, they sent me email saying we cannot come. So like they have the money, but so anyone that comes, they seem to be very positive. I think that's what happened because he was not selected. But the Korean guy was